Welcome to the 2021 Photonic Spectra Optics Conference, a showcase of this year's industry innovators along the global optics manufacturing value chain. You're joining us now for Optics for High Power Laser Applications, presented by Excelitas Technologies Corp. Presenting on this topic for us today is Trey Turner, Vice President of Engineering for Excelitas, responsible for R&D in Boulder, Colorado. In his previous role as CTO of Research Electro-Optics, now part of Excelitas, he oversaw innovations in the field of laser optics and the associated design, manufacturing, and test methodologies. In this presentation, he's going to provide an overview of the state of the art and key aspects of laser optics design, manufacture, and testing. At any point during the presentation, you can leave a question or a comment for us in the chat on your screen, and if we don't respond to you during the conference, we will follow up with you later by email. And if you missed part of the presentation today, you can return later and watch it on demand. So with nothing else from me, I'd like to introduce Trey Turner. Welcome.
Good morning. My name is Trey Turner. I'm the Vice President of Engineering at Excelitas Technologies. And today I'm going to talk about optical technology for high-powered laser applications. Now I'll start the talk with a brief introduction to Excelitas Technologies and then a quick overview of the specific laser applications that are within the scope of this talk. Specifically, we're talking about very, very high-power laser applications. And then I'll talk a little bit about the system characteristics that tend to be driven by the optics technology within the systems and the particular specifications of those optics that tend to be the biggest drivers of the key system characteristics. And then I'll finish up with a little bit of an explanation of some of the key trade-offs that we often encounter when we are specifying laser systems and the associated optical technologies. Excelitas Technologies is a global organization, sites all around the world, focused on photonics technologies. It was born about 10 years ago with a carve-out from PerkinElmer that incorporated a number of former organizations like EG&G and Redicon, pieces of RCA, lots of diverse photonics technologies that then a few years later merged with Key Optic, which has its own storied history of photonics organizations, and then few acquisitions after that to create the organization that we have today. I personally represent the company that was formerly known as Research Electro-Optics, or REO. Our business is divided up about a third defense and aerospace and about 2/3 commercial business. We've got almost 7,000 employees worldwide, so a very substantial and diverse organization. At the Excelitas site in Boulder, Colorado, that was formerly REO, we design, develop, and manufacture optics and assemblies and optical modules for a wide range of applications, a wide range of system types, but a pretty significant concentration of applications in the laser photonic space. Now, in terms of the laser application space, there are really three specific applications that I think are representative of the kind of very high power, very high intensity laser systems. The first being directed energy weapons, sometimes referred to as HEL or high energy laser for military applications. Now, these are usually continuous wave lasers. They're usually around a micron wavelength or so, but they're very, very high power, anywhere from 10 kilowatts up to 100 kilowatts or even higher. And in addition to that, sometimes they have multispectral requirements, that is to say additional bands beyond just the primary laser band that have to be handled within the optical system. And this can create its own set of challenges. The other application, or the next one, is high power industrial lasers. And now these are also typically CW lasers, generally used for cutting and welding and operations like that. Their power levels are a little bit lower, somewhere in the neighborhood of 5 kilowatts to 20 kilowatts are typical. And they tend to be more compact, and so their fluences and intensities can still be extremely high. They also have special requirements for cost and reliability because they tend to operate with very, very high utilization around the clock, all week long. So there's a significant reliability challenge with these kinds of systems. The third field is very high power scientific lasers. These are usually short pulse lasers, femtoseconds, nanoseconds, very high energies, kilojoules to megajoules, low repetition rates, usually just one shot at a time, and in some cases very large optics. So the main concerns for this one are going to be very short pulse performance. Now the laser characteristics for these applications that are typically the most critical as they relate to the optical specifications are the beam quality, throughput, reliability, and what's typically referred to as swap C, which is size, weight, power, and cost. Now, the beam quality is typically, we're talking about the distribution of the beam, and that gets to what the range of the laser is going to be, what the spot size can be, how high quality that spot is going to be, and how quickly it's going to act. Because usually a smaller spot is going to have a faster effect than a larger spot. The throughput is in this context, I'm going to use it a little bit of a squishy sense. It could mean how much power we can get through the system, and it also can be like what's the efficiency, what's the fraction of the input power that's going to get into the output power. Also important for the range, obviously, and it's going to be relevant to the size of the system too, because obviously if we need to have a very high throughput, we're going to end up with a larger system. Reliability is going to drive maintenance intervals. It's going to drive cost in important ways, and it's going to drive the environments that the system can operate in. And then of course the swap C, self-explanatory for the most part, but for military applications it's quite important because mobility is a key concern, and of course cost always has to be in mind. Those four characteristics will typically be driven by 7 specifications that we need to pay attention to when we're defining an optic for a laser system. The laser damage, how much fluence the optic can take before it's going to damage. The surface quality, what are the size and number of the defects, point defects and scratches. The absorption, how much of the light is going to get converted into heat. The reflectance and transmittance, how complex is that spectral band? How high a level of reflectivity are we going to have? The stability and durability, how dense and durable are the films or the optical materials? And then the size of the aperture, obviously a critical part of the specification, and then how precise the surface figure requirement is for any particular optic. Now these specifications are typically going to inform our choice of materials and processes for these optics. And so I'm going to go through a few of these specifically here now. The first 4, laser damage, surface quality, absorption, and the spectral requirements, and then also summarize some of the trade-offs that we normally see in those and in the materials and processes that are used to produce these optics. Now, laser damage is certainly one of the most interesting specifications that we have to consider when we're specifying an optic. There's lots of confusion, lots of ongoing research on the subject, and a lot of things that just still aren't fully understood, not just by individual manufacturers, but by the research community in general. It's clear that we have separate mechanisms, different mechanisms for pulse laser damage versus continuous wave damage. For pulse damage, we're typically going to be more concerned about nonlinear absorption, multiphoton absorption, and the material characteristics associated with that are very important. So the band gap of the material is key. The band gap, as it happens, relates also to the refractive index. And so there is a very well-defined relationship between the refractive index of the material and the laser damage threshold of a given material. And that has a fairly significant impact sometimes on the thin film design space that we can work with when we're designing coatings for pulse laser damage mechanisms. For CW damage mechanisms, really it's the linear absorption that's key. Here we're looking at thermal effects usually. Sometimes the thermal runaway types of effects are really critical. So we're going to focus in on the linear absorption, and then finally for both categories of laser system, the defects are typically going to dominate. So most of the damage is actually going to occur at defect sites. Now that can be enhanced by these other things. So if the linear absorption is high, or if the band gap is too low in CW and pulsed applications respectively, what's going to happen is the defect is going to enhance that. It causes a field enhancement effect that's going to induce damage at a lower threshold than would normally be the case if the defect was not present. And because defects tend to be sparsely distributed across the surface, the statistics of that are very, very important. And it's extremely important to understand how the defects are distributed across the surface and how our test is going to uncover the potential damage from those defects. So naturally, one of the key specifications when it comes to laser damage is surface quality. There is a direct relationship between the laser damage performance of an optic and the surface quality, and that goes beyond any particular laser system type. Most laser damage is initiated at defect sites, and defects that are really small, smaller than you might think, can lead to laser damage or be statistically meaningful in the evaluation of laser damage probabilities. As a rule of thumb, based on some previous work that we've done, we find that a 10 micron defect has a damage probability of about 50% at 50 joules per square centimeter for a 20 nanosecond laser pulse. 20 nanoseconds is a common reference point for pulse laser damage. And it's important to understand that all of this is statistical. There's always a probability. We're testing with very, very poor coverage of the surface, and so we're only getting a small glimpse of the actual damage performance of any given surface. But as a reference point, the kinds of specifications, the kind of fluences that optics could be expected to withstand well-designed, well-manufactured optics at 1064 is around 50 joules per square centimeter for 20 nanoseconds. Now that is highly dependent on the type of coating. It's highly dependent on the spot size and the aperture size that's being tested and being used. But that's kind of a decent rule of thumb. When we're in the CW regime, it's a little bit more squishy. The data is a little bit more scarce, but something in the neighborhood of 10 to 20 megawatts per square centimeter can be expected to be acceptable for most high quality, low absorption, high surface quality laser optics. But if we want to be successful in specifying these kinds of optics, we have to minimize defects. That's got to be a critical requirement. We've got to understand the apertures so that we're not over-specifying, trying to specify defects, minimal defects over very large apertures. It gets cost prohibitive very quickly. So we need to understand very clearly what the aperture sizes are and the fluences at different places within the aperture size. And of course, properly specifying the test is one of the most challenging things that we do. But making sure that we're clear about the spot size and how many sites are going to be tested and what we actually know based on the result of that test is going to be a key consideration. In general, I've got this little this little trade-off diagram here down in the bottom right, and basically what I'm indicating here is that if we prioritize surface quality in a given specification, and that's kind of what I mean by the big blue arrow. Then we're typically going to improve also the laser damage and the durability. Those things tend to go together, but of course at a higher cost, right? So that's the yellow arrow pointing down just means that the cost is going to get worse if the surface quality gets better. The next specification that we need to be paying attention to, particularly for CW applications, is absorption. Now, absorption can come from many different sources. There's lots of different mechanisms, but luckily it can be pretty low at 1064. If we're making optics out of very high quality materials and using the best processes, we can actually get into the single-digit ppm level of absorption on a fairly regular basis. In fact, as low as 1 ppm. And this is going to be at a level that really is typically not going to be problematic then for thermal effects within a laser. There may be localization of that absorption around defects that could be more problematic, but as a general rule, in the quality of the film, if you're in the neighborhood of a few ppm, typically speaking, that's not going to cause enough heating to be problematic. There are several different ways to measure absorption, and this is something that's often debated. we have a preferred method for this level of absorption, which is called photothermal common path interferometry. It's not the most accurate method, but it's highly sensitive. So if we're trying to measure absorption levels that are around 1 part per million, it really is the method of choice. If the absorption level is expected to be higher, there are other methods that are more accurate. Calorimetry in particular can be done with a very high level of accuracy, but its sensitivity starts to get somewhat challenging and or prohibitive around 10 parts per million. Spectrophotometry is commonly used for absorption, but it's really only appropriate for much higher levels of absorption. Now, when we're optimizing absorption, we need to obviously maintain high purity of the materials. We're typically using ion beam sputtering. That's where we can get these absorption levels that are down around 1 part per million. We have to be careful about OH, water content of the various materials. And we have to think about how we're going to post-process the materials. When we do all this stuff, we will see the absorption improve. We will typically get good CW laser damage coming along with that. The pulse laser damage may actually decrease a little bit because the material choices are usually not the same. And we could be challenged with some multispectral requirements because of the complexity of the films that would be required for those applications. So the spectral requirements are sometimes the thing that can require the most optimization and refinement to make sure we're going to get the best performance, going to get the optimal manage the optimal trade space for a given application, particularly when we're talking about managing multiple bands in an application. There's an example on the screen here of a single band reflector, and I'm just putting this down here to give you an idea of what can be achieved if we only have to worry about one wavelength. This is a typical quarter wave stack. The plot at the bottom right is sort of a schematic representation of the design of that. So this is just a sequence of about 33 quarter wave layers. This particular one is made out of tantalum pentoxide and silicon dioxide. And with this simple design, we can achieve reflectivity levels that are almost 99.999. They're actually 99.997. So a lot of very high reflectivity. The thickness of this design is very manageable, about 5 microns total thickness, and its absorption levels are very low. It can be made with very high surface quality. So this is going to be a really, really high quality reflector for a laser application. Unfortunately, it only reflects in one band. So if we want to be able to manage multiple bands, obviously we've got to get a little bit more sophisticated in our design. And that's where things can get pretty tricky. Here's an example of a multi-band reflector that has bands in the visible. It has a pretty wide band in the near infrared in order to accommodate a spectrally beam combined high energy laser source. And then it's got another reflection band up in around 1700 nanometers for some other laser functionality. Putting all three bands together, having the width of these bands be fairly critical, creates a pretty challenging design problem. And you can see the one example of a design that would be used to deal with this down there in the bottom right. Much more complex than the previous one. This one has about 200 layers if we use the same materials. The reflection can still be pretty high, but we do have to sort of choose between the bands and make sure that we're focused in on the right band that matters for laser damage. This is a pretty costly coating, and when we do a coating that's this thick at a level of about 20 microns, this one's actually 21 micron design thickness. It's a long deposition time. That actually introduces some compromises with laser damage as well, because there's more opportunity for defects to get introduced into the process. So the surface quality limitation may start to be an issue with a design of this length. So we have to prioritize the bands. We need to be careful not to overspecify the reflectivity. If you can deal with a lower level of reflectivity in some of the outlying bands and just focus in on the primary band, you can typically optimize the trade-offs and get to a pretty acceptable trade space. But as we increase the multispectral performance, we're going to compromise on the rest. We're going to compromise a little bit on the primary band reflectance. We're going to compromise a little bit on laser damage. Figure control is going to be a challenge because these thick coatings carry a lot of stress, and so now we've got to really pay a lot of attention to how we're mitigating that stress or compensating for that stress in one way or another. Now we're going to talk about the materials and processes that we use to produce optics to these various specifications. We'll talk about the substrate materials, the polishing processes, and the coating processes. We'll start with the substrate materials. There are 4 commonly used substrate materials in these high energy laser applications: fused-silica, silicon, silicon carbide, and aluminum. Each has their own advantages and disadvantages. And we'll just talk briefly through each one just to get a sense of where these are typically applied. Fused silica is the most optically pure of the materials. It's typically used for transmissive optics and for reflective optics where the thermal expansion coefficient is really a key consideration. Fused silica lends itself very well to very high quality polishing. So for the most critical optical requirements where surface quality, surface roughness, scatter are the most important aspects, fused silica is a common choice for those things. It's usually not used in larger spherical, aspherical optics where the density, the weight, and the stiffness can start to be an issue. Its specific modulus, or the relationship between its stiffness and its density, is not really favorable for making light-weighted optics compared to some of the other materials. Its thermal conductivity is also quite poor, but its thermal expansion coefficient is quite favorable, which means that not only is it very thermally stable in various environments, but it also lends itself well to stress compensating coatings, which typically depend on the thermal expansion coefficient of the substrate material. Our second material is silicon. Silicon is a general purpose material that is used when high optical polishing quality is required, but also thermal conductivity is key. It forms some sort of a middle ground between some of the other materials. Doesn't necessarily excel in any one area, but it has a nice balance of the specific modulus and the thermal expansion coefficient, thermal conductivity, and cost, which are key considerations. Silicon carbide kind of represents the ultimate in a few of those areas. In terms of the specific modulus, its stiffness relative to its density, its ability to perform as a light-weighted material in very demanding environments, it really is second to none for those applications. Its thermal conductivity is also outstanding, and this is really why it's valued for these particular applications. It's challenging to polish. It's a very hard material, which means it's costly to polish, but often for some of the most critical optics, that's a trade-off that's worth making. And so it's usually used in the larger optics or things that maybe are in motion or where the weight is a really key consideration. Another material that's used in similar environments is aluminum. It comes with significant trade-offs in terms of the specific modulus and its ability to support very high quality polishes. But it has outstanding thermal conductivity, and its cost is really highly favorable. It's an inexpensive material. It's inexpensive to work. It can be diamond turned, and there are techniques for polishing it to a pretty reasonable quality that can be acceptable for some of these applications where the trade-offs really do end up making sense. Now, in terms of the polishing processes, this is going to depend on a number of factors, starting with the substrate material and the shape and form factor of the optical element. So for a small optic that has a very high demand for surface quality, roughness, scatter, surface finish, those kinds of things, conventional polishing, pad polishing, and pitch polishing are going to be outstanding processes for that. They're going to start to break down when the optics get a little bit larger. When the surface form gets a little bit more demanding, farther away from spherical or flat surfaces, that's where we start to get into some of the more deterministic and flexible processes like like robotic or computer-controlled polishing or magnetorheological finishing, MRF. These processes, in the first case, robotic polishing is actually a polishing process, and therefore can turn a ground surface into a high-quality specular polished surface. MRF is a finishing process, which means it doesn't technically polish the surface, but it can correct small errors in the surface. So these things can be used as complements to one another, and commonly are when there is a demand for a very challenging surface form that has to be held very precisely, maybe corrected for coating stresses and things like that. You typically won't achieve quite the surface quality, the surface roughness characteristics, in some cases the mid-spatial frequency or the waviness quality that you will get with the more conventional processes like pad polishing or pitch polishing. But in some cases, that's really the only option if we're talking about larger optics that are that have non-spherical form. We're typically going to be going to one of those other processes. And then finally, the coating process. There are a number of trade-offs and considerations here as well. We'll start with the evaporation process. This is really the most conventional, most commonly used, in some ways the most cost-effective, although that's not always true, process that's out there. And this just involves evaporating the source material and condensing it onto the substrate surfaces. It's a good general purpose process. Where it really shines, though, is when we have significant out of band specs. If there's a lot of infrared requirements, or if we're getting into UV requirements, sometimes the material choices will be such that it'll be desirable to use an evaporation process, because it is the most flexible in terms of the palette of materials that we can choose from. It has significant trade-offs in terms of the accuracy and the control, the surface quality that's typically achieved. Can be challenging. The durability can be challenging. And we certainly won't get the low levels of absorption that we'll get with the more energetic processes, but it comes with other trade-offs that sometimes can be a benefit. One of the things that we often do to try to improve that while maintaining a lot of those benefits is add some kind of ion assist or plasma assist into that process, and that just amounts to putting a particular kind of ion source, plasma source, into the chamber and adding some energy into the deposition process. This can improve the film quality, the density of the films, the durability of the films. It also improves the consistency and thus the accuracy and control of the process. It can reduce the absorption significantly so that we can get down into the sort of 20 ppm level. And that can be favorable for certain applications, and particularly if we're trying to get better films on larger substrates. This is typically one of the processes that will apply to that. The next process on the list here is a magnetron sputtering process. This is sort of a progression from the standpoint of film quality. This is going to be kind of the next step beyond the ion-assisted deposition. In this case, now we're using energetic plasmas to sputter off the material and deposit onto the substrates. It's typically in fairly close proximity to the substrates, although there are methodologies for having it be farther away. And the proximity to the substrates can cause challenges in terms of maintaining high surface quality. So we don't always get the ultimate in terms of surface quality, but we do get decent absorption. The rates are good. It's a good general purpose process. But the ultimate in terms of film quality, if we're talking about wavelength ranges from the visible to the mid-infrared, is going to be ion beam sputtering. And that really has unmatched surface quality capability, unmatched absorption, and the density of the films, and thus the stability and durability of the films, is also really exceptional. So that's really our workhorse technology for this type of application. Most of the laser optics that we produce will be made using ion beam sputtering, and there are technologies for doing that up to 300, 400, maybe in some cases 500 or 600 millimeters in diameter. So it's really applicable to all but the largest optics in these systems. Now I'm just going to summarize a few of the key trade-offs that come out of those come out of that understanding of the manufacturing processes and the materials and where we go with the specifications. So I've got a few examples here where we prioritize different aspects of the system and see what the compromises need to be. So the diagram here should be read as the blue arrows that are pointing up mean that we're prioritizing that thing and we're actually driving those things up on purpose. The yellow arrows pointing down means those are probably areas we might have to compromise or we need to be aware of some kind of a trade-off. And then the gray arrows pointing up typically just mean that we're going to get some benefit for that, even though it may not be the thing that we're prioritizing. So for throughput, of course, we want to have the biggest aperture that we can. We want to have the lowest absorption that we can. We want to have the highest reflectivity that we can. We want to have the highest laser damage that we can. Those are all the things that go into high throughput. So that means that we're going to want to have the best quality films, high reflectivity. Those things can challenge the surface figure a little bit. So we're going to maybe see a little bit of a sacrifice of the beam quality. Now on the flip side of that, as we drive the absorption up, we actually get a significant benefit to the stability of the beam quality because we don't have to deal with the thermal effects that we might have if we were dealing with high absorption. All right, so that's a little bit of a trade-off as we start to increase the throughput. If we're naturally driving the absorption down, we get some improvement in the stability of the beam quality, even though maintaining it in the first place might be a little bit more challenging. We'll also incur more cost. As the aperture size gets bigger, everything gets more expensive. And of course, the higher performance absorption and reflectance are going to drive cost as well. Now, if we decide instead that we want to prioritize beam quality, then of course we're still going to go for the maximum possible aperture size. Now we're going to drive the surface figure, and the surface figure actually is one of the more significant cost drivers. It is in some ways the most expensive thing to maintain on large surfaces, so we need to be careful with that. And then of course absorption, as I mentioned before, has such an impact on the stability of beam quality that if we're concerned about beam quality, we're probably going to prioritize that. In trade for that, we're probably going to have to give up a little bit of the reflection and transmission performance. We might sacrifice the laser damage performance just a little bit. And of course, as I said, the surface figure being one of the most expensive dials to turn, we will probably compromise on cost a little bit as well. My last example here, if we do want to prioritize size and cost, if we want to make a compact, cost-effective system, then there's a few other things we might prioritize. In this case, we'll probably want to shrink the aperture. Now we're going to give up a little bit of throughput and beam quality when we do that, but if we push up the laser damage, we push up the reflectance, we can hold the throughput to a pretty good level, and we're just going to have to be dealing with the the diffraction limit kinds of challenges that we get with a smaller aperture. The surface quality can be maintained at a pretty high level because you've got a small aperture. So we'll benefit in many ways by shrinking the aperture a little bit and increasing some of the component requirements like the reflectance and the laser damage. We actually get an overall cost benefit to that because there's such a huge cost lever on the size of the aperture and maintaining the surface figure. So those are things that we'll need to consider if we really want to optimize cost in a system like this. I hope you've enjoyed the talk. A few quick takeaways. It's important to specify the components that are going into a laser system if you really want to optimize the performance. You don't have to know everything. You don't have to know every aspect of optical manufacturing and thin film processing and design and all that kind of thing. But having a basic sense of how these various requirements interact and what the methods are and the trade-offs associated with that is really the key thing in order to make informed trade-offs. You don't have to know everything, just a few critical factors that we've addressed here in order to have the most possible success in designing and building a laser system. Thank you very much for your attention. I've enjoyed it thoroughly, and I hope you have a great day.
Thank you very much, Trey. To everybody in the audience, if you have a question for Trey, please feel free to write it into the chat. And if we haven't answered you already, we will reach out to you later with our reply. So thanks for joining us for Optics for High Power Laser Applications presented by Excelitas Technologies Corp. This is part of the Photonics Spectra Optics Conference hosted by Photonics Media. Thanks so much, Trey Turner.